We are now into week number 3, and hopefully, I think there were a few minor issues with Git for the exercise today, but I think I hope that you've been able to submit your exercise number 2 without too many problems. And in our third week of the course, our plan is to move into talking about the diffusion equation, and we'll first have a little bit of background and theory about the diffusion equation, kind of how it works and how to understand what it's able to do for us. And then we're going to be introduced to our first lesson on thermochronology. So this week is going to be a little bit different than the previous 2 weeks in the sense that I have lecture slides here for the first part of the lesson for today. I'd also like to demonstrate a few things in a Jupyter notebook just to show you some things that you might want to use for this week's exercise. And then I'll talk about the exercise when we get there. You may have noticed on the course page that the exercise is not yet posted. I have been working on a new exercise for today, and I did not quite finish it before needing to switch over to our class session. So that will be coming. I hope that I'll have that up later this evening. So I'm sorry about the delay with exercise number 3, but I can assure you it's being revised with the aim of being a little bit more in line with some of the other exercises later on in the course. And I think this will be a significant improvement with the revised version of exercise 3. It just happens that I haven't rewritten an exercise from scratch in a few years, and I just simply didn't plan enough time to get the thing fully written and tested. And it does need to be looked over carefully before I let it loose to all of you. So don't see any additional feedback here. And yeah, as I mentioned, we're going to talk about the diffusion equation today, and we can get started with first some slides about the diffusion equation. And that'll hopefully give you some idea of why it's a useful equation for us to talk about in general. Let's see here. Hopefully the slides look okay now. I guess you can see, maybe if someone wants to just put a message in chat that you do see the slides themselves and not my presenter view, that would be helpful just to confirm. But I assume, since I'm sharing my laptop screen, that you're seeing the same thing I am. So yes, we're going to talk about diffusion. And the first little bit of what we'll talk about today is some theory and examples. So it might not be super exciting to you at first, but this is the first equation that we're really going to kind of take apart and explore. And part of the whole motivation for a course like this one is to help you in looking at things like equations you might encounter in textbooks or scientific journal articles, and not just freaking out when you see the math and kind of shutting down, because I've been there. I'm sure some of you have been there too. But rather kind of, taking a breath and just taking a look at what the different terms are in the equation and picking it apart and trying to understand how it works. So for us in the lesson at the beginning here today, we'll just talk about the concept of what diffusion is as a process, and then we'll look at the mathematical definition. And I think I kind of walk you through a little bit of how the equation works, but we don't really go through too many derivations or things like that. I try to kind of stick more to understanding the terms and how they might affect the diffusion equation. So let's start with the concept, and maybe a good place to start just with that is, why do we even care about diffusion as a geological process? And here are just a couple examples of a diffusion type of process. So there are things related to the rheology of rocks and how the crystals deform at the atomic scale. That is essentially a diffusion-like process. So this has to do with how rocks and minerals are deforming in the earth. There are also erosional processes that they behave kind of like a diffusion process. So here's an example of something that you might not even think of as an erosion process, called rain splash. And this is what happens when a raindrop strikes the Earth's surface. And of course, when it strikes, it does eject some material away, just like a small kind of impact crater in a sense. So this raindrop comes in, strikes, and scatters some material away from where it strikes, and it tends that more of that material goes downhill than goes uphill, which essentially behaves like a diffusion process. And then finally, another example would be if we look at, this is closer to the topic of thermochronology, which we'll get into today. I'm not assuming you know anything about that. But essentially, what's occurring with many thermochronometers is that we have some kind of daughter isotope, something that is produced and trapped within a crystal that is diffusing its way out to the outside world at the edge of the crystal. And that diffusion process and how long it takes is something we'll get into in terms of what we can learn about the history of rocks from things like how long it takes for helium to diffuse out of the center of an apatite crystal to its edge. So those are just a couple examples. If we want to put a definition to the term diffusion, this is a process that results in mass transport or mixing as the result of random motion of diffusing particles. Now, that might not seem immediately obvious why random motion is going to do something like diffusion, but we can look at this with a little example here. So this is just a animated GIF that I'd found somewhere online. You can see the source down here in the bottom right of two different particles here. There's atoms of A and atoms of material B, and they're colored blue and yellow. And currently, in the starting stage, there's this red boundary between the two that's dividing them such that all the atoms of A are on the left and all the atoms of B are on the right. Now, this is somewhat like a crystal in the sense that there is a regular grid where the particles can be. They can either, they have to be in one of these little positions that are regularly spaced between one another. And this animation is essentially going to show us what happens when we take away the barrier between A and B and allow random movement of the particles between different positions. So, for instance, at some location, let's pick one that's maybe a bit better, somewhere here, you can basically go to one of the surrounding places. You can either go to the spot above or below, or to the left or to the right. And as that process occurs, we'll see how A and B begin to mix with one another. So when I click on this, what you can see, and this should, I think, just kind of keep replaying, is that over time, the boundary between where there are or are not any particles of material A or atom A is moving off to the right with time. So as a result of this random motions, just kind of flipping between different positions, we do see, in fact, that there is sort of an advancing front of particles of atom A moving off to the right. Same thing is true for the material B moving to the left. And this boundary between the two was once a very steep gradient, right? That there was nothing of particle B on the left and no atoms of A on the right. It's gradually becoming more and more mixed over time. So that's what this concentration curve is showing down below. So this is the concentration of atoms of A. And you can see that over on the left side, even toward the end, it's still got a full concentration of atoms of A. But over time, as you're closer to this boundary, that concentration is decreasing on the left side of the red line and increasing to the right. And that's because the particles of A are moving off to the right as a result of the random motion. So that's essentially how diffusion is operating. Probably you've already seen things like this. And what this is also showing is that there's some relationship between the distance that the material has diffused away and the square root of time. That's something we can perhaps come back to later. But our concentration gradient is essentially this boundary between the two materials. And you can see it starts out as almost infinitely steep, and it's gradually getting shallower with time. And again, that's because of the mixing that's occurring. So that is why we talk about this random motion of diffusing particles thing at all. And what you tend to see here in terms of a net motion is that you have transfer of material or energy from regions of high concentration to regions of low concentration. So heat conduction is also a diffusion process, and the tendency is that heat will be transferred from areas that are hot to areas that are cold if we have a concentration of something like perfume that you can smell. Of course, if we were to open a bottle of perfume in one corner of a classroom and just leave it sitting there, the material would gradually diffuse. The smell of the perfume would gradually move into the room. And that's because the concentration is high near the bottle of perfume, where there's perhaps some kind of evaporation taking place, and low further away. The thing is, as this process occurs, is it tends to reduce concentration gradients. So when we have a barrier between two materials like A and B at the beginning, we have this essentially infinitely steep gradient. But as soon as we take away the barrier, then the diffusion process starts occurring, and the concentration, the gradient between A and B, reduces as a result. So that was our kind of conceptual definition. We can make this a little bit more quantitative. And the way that we would do this is to add a little bit more precise terminology. So another definition we could give would be that diffusion occurs when a conservative property moves through space at a rate proportional to a gradient. Now, some of these words might sound familiar, but to me, if I was to read this sentence as it is presented to me now, I might not fully understand what this is talking about. First off, conservative property might not be something that's jumping out to you as like an immediately familiar term, but this is a property that must be conserved in a system. So for instance, if we're dealing with an ideal world, we might assume that the energy is conserved as the result of a diffusion process. So we're not creating or destroying energy as a result of diffusion. We're just distributing it differently. Same thing would be true of mass. If we looked at that example of particles of A and B mixing with one another, we're not creating mass or destroying mass. We're simply just trading places. And as a result, we're conserving mass in that example. The rate proportional to a gradient part might sound a little bit more confusing in a sense, but all it's saying is that the movement occurs in direct relationship to the change in concentration. So again, if we have a hot piece of metal that's put in contact with a cold piece of metal, at the boundary between the two is where we'll have the most rapid changes in temperature, and further away, the temperature changes will be more gradual with time. And that's because the gradient is steepest right where the two pieces of metal have been put in contact with one another. And as you go further away, the gradient decreases. And so the heat transfer, or the rate of change of temperature, will also be lower in that case. So that is our kind of rough working quantitative definition that we'll hopefully now start to understand a little bit more by looking at the mathematical piece to that. So we've had this kind of descriptive terminology, and now we can look at how that would be converted to something more like an equation. So here's our definition. So we have the same thing we just saw. I can't see my mouse cursor for some reason. I don't know where it's gone, but otherwise I would highlight this. And anyway, we can see that our diffusion occurs when a conservative property moves through space at a rate proportional to a gradient. So let's focus first on this rate proportional to a gradient piece. So in things that are familiar, we could say something like the transportation rate is proportional to a change in concentration over some distance. This is basically saying the same thing. The rate proportional, it would just call it transportation rate. And the gradient we could call a change in concentration over some distance. Okay, that's hopefully not too bad. We could replace our transportation rate term with another more technical term called a flux. It's just a way to basically say the same thing. And here we would say that our flux is proportional to the concentration gradient. That actually looks a bit more like the original definition that we had. The nice thing about this is now we're moving in a direction of more mathematical terms as well. Flux is something we often indicate with the letter Q. Now, lowercase q is often used to refer to a flux. Could be a flux of energy, flux of heat, or a flux of mass. And a concentration gradient is going to tell us something about some kind of change in concentration over some distance. So if we were to replace this now with mathematical symbols, our Q, the flux, is proportional to, that's the sort of alpha-looking symbol, the change in concentration, delta C, divided by some distance delta x. Okay, x can be, could be any distance, doesn't have to be horizontal, could be vertical, whatever. It's just some distance delta x, and the concentration here we're indicating with capital C. So this is basically how we're going to go from converting our kind of glossary or dictionary definition to the form of an equation. Now, often when you have something like a proportionality, so we say Q is proportional to delta C over delta X, the proportional to part can often be replaced by some kind of scaling factor, and then we can set the two sides equal to one another. So we can do that here, for instance, and we can make one other change at the same time. But first, we could replace our proportionality symbol with being equal to minus D. So D is what's called the diffusion coefficient or diffusion constant or diffusivity. Kind of goes by several different names depending on what context you're referring to it. And you can see that the capital deltas have been replaced by these lowercase deltas, the partial differential operator. So essentially that's just something that says, okay, let's go from some finite difference, delta C, so like C2 minus C1, and just make that a sort of infinitesimally small difference. So that's essentially just saying that the value of delta C gets smaller and smaller and smaller, and we represent that here with the partial derivative C over the partial derivative of X. So here delta X would be some finite difference in the distance, and the partial X would be an infinitesimally small distance between 2 points. And don't worry too much if this is not entirely familiar to you. Now, if we go back to the example we had before with our little animation, we had atoms A and B, and we could formulate, for instance, the diffusion of the atoms of A across the red line with time as Q being equal to minus D times the change in concentration of A over some distance delta X, which would be very close then to this boundary between the two materials at the beginning. So that would be essentially our way of applying that. Now, what does that mean? Well, we could take a look here, and we could take a look at a couple things, including why is there a minus sign? To do that, I think it's better that we jump back to the world of finite differences. So we'll go back to having big deltas and see our equation in a very similar way, but that is that we just look at two different points. Let's look at a point X1, where the concentration begins as concentration C1 of atoms of A. And then there's another point further over on the x-axis called X2, and that has a concentration initially of C2. And you can see the 2 points, you can see the colored dots here. I'm going to just see if I can get my mouse cursor to come back because I'm tired of not being able to see. So just give me 1 second here. I think I should be able to see my cursor. And you should be able to see it. There we go. It's back. So yeah, I hope that you can see the cursor. Maybe you can, I hope. But the point here is that if we look at these 2 points, X1 and X2, we can see the initial concentration of the atoms of A indicated with the different dots that are here. And if we were to take this and put it into our equation, what we see is that our equation would say that we have Q equals minus D times delta C over delta X, which is C2 minus C1 over X2 minus X1. Here, if we look at it, C2 is something like 0, minus C1 is a number that's positive, so this is going to be a negative term on the top. X2 is bigger than X1, so that's going to be a positive term on the bottom. So this sort of fraction part of our equation is going to be negative. And then when you multiply that by negative D, you come away with a positive number, which means that our positive flux along the x-axis is shown basically, as you can see, the material A is moving off to the right. That's our flux of material off to the right with time at some position here close to the middle of this example illustration. So that's why we have a minus sign there, because basically when you plug the numbers in here and you start looking at things, this is how we end up with a positive flux, is by having a negative D, because this dC or delta C over delta X term will be negative in examples like this one. All right, we have one other piece of our equation we have to look at here and our mathematical definition. That is the conservative property moving through space part. I've once again lost my mouse cursor. So yeah, when we talk about this, our conservative property moving through space, it's a little bit harder for us to translate, but the conservative property we could consider as a change in concentration with time that is equal to a change in transportation rate with distance. Now, that probably doesn't make a great deal more sense, but essentially what we're saying is that the change in the concentration at some time is equal to how the rate of transportation is changing with distance. Said slightly differently, we could say our rate of change of the concentration is equal to the flux gradient. So now we have things that sound a bit more like what we saw before. Remember, flux was indicated with the letter Q. Now we have a flux gradient, which would mean that we're going to have our change in Q over some change in X, for instance. And our rate of change of the concentration would be indicating that the concentration is changing with time. So that would be something like delta C over delta T, which we can indeed fill in here to say that our change in concentration, delta C, with time over, so here it is, over delta T equals minus dQ or delta Q over delta X. That's just converting what was said in the terms used in our definition to the mathematical equivalent. Delta Q over delta X is a conservation of mass. So that's why this conservative property moving through space thing, that's where that comes in, is that the right-hand term is essentially a statement of the conservation of mass. How does that work? Well, I think we can relatively easily understand this through an example. So let's consider that our delta Q over delta X can be expanded to be Q2 minus Q1, just the same that we did with C2 minus C1. And our X2 minus X1 is the same as it was previously. So we have two fluxes at two different points, X1 and X2. What's going to happen here if the flux at Q2 or position X2, the flux Q2 is larger than the flux Q1? I don't know if somebody wants to answer this in chat, what they think would happen here if this was the case. But what happens if Q2 is bigger than Q1? And maybe while you think about that and consider putting an answer into chat, I will try once again to get my mouse cursor to come back. Probably I have to do some kind of setting here to make this work. Any ideas here why the well, I guess I've made the slides disappear now, so 1 second. I think I have set things up now so my mouse cursor won't go away. But yeah, what's going to happen here in terms of our equation? So we've got delta C over delta T. Let's assume delta T doesn't change. So what's going to happen to delta C here if Q2 is bigger than Q1? So I won't make you suffer through this because we do have another topic to talk about today. And so I'll push things along here. But of course, if Q2 is bigger than Q1, then this top term is going to be positive, right? Q2 is bigger than Q1, so Q2 minus Q1 would be positive. X2 minus X1 is going to be also positive if we take the same example that we had before. Now this has got a negative term here. So if the flux at Q2 is bigger than the flux at Q1, then this whole term is positive. And so then when you multiply by the negative sign out in the front, you end up with the concentration decreasing with time. So if more mass is being fluxed away at Q2 than Q1, it would suggest that our concentration would be going down with time. Same thing is true if Q2 is smaller than Q1, that our concentration will be going up with time. And that's basically how this then becomes a conservation of mass, is that these two flux terms will determine what happens in terms of the change of the concentration of atoms of A or atoms of B, or of thermal energy, or of any other number of things, some isotope, whatever you want. So that's basically how that's working. Now, if we take our finite differences of the big deltas, replace them with the sort of infinitesimally small difference with the partial differential operator here, we can take the same equation that we had before. So now it's delta C over delta T, or partial derivative of C over partial T minus partial Q over partial X. And all this says is that the concentration of A is going to change based on the flux across some position minus the flux at some other position, X plus delta X. So if we were here in the middle, or maybe just slightly to the right of the middle, we see that the concentration is going down. And if we're some further distance over here, X plus delta X, the concentration, well, I guess if we're looking at concentration of A, concentration is actually going up over here and going up slightly slower to the right. But you can see as a result of the two fluxes that the concentration change will be such that it's going up further and further to the right with time. So you may want to look over the slides again when we're all said and done here, but the slides are up on the course page and you can have a look at those there. I'll show you when we get finished with the lecturing part of today's lesson. I'll show you where to find the lessons slides. So in the exercise for this week, we'll explore some simple models of diffusion. We'll do things like kind of calculate these type of diffusion curves and look also at some of the factors that need to be considered when we apply diffusion to geological examples. So that'll be the first part of the exercise for the lesson number 3. I think, yeah. So we're basically ready to move on to our next topic. I'm going to pause here in just a second for if there are questions. But what's coming up next is we're going to be taking our first steps into looking at thermochronology. You'll see, I think, throughout the next few weeks why this is something that's interesting to consider in this course. But essentially what we're going to do now is look at a way that we can apply the diffusion equation to look at the ages of rocks and how that relates to cooling of rocks as they're exhumed toward the Earth's surface. And the method is called thermochronology. And we're going to see, basically for the rest of the course, we'll see bits and pieces of concepts related to thermochronology. So you don't need to try to understand everything in the lesson today about thermochronology. We'll come back to that several times now in the remaining weeks of the course. But yeah, at this point, I haven't really seen any signs of life in chat. So I'm going to ask you maybe to give me some ideas here of what are some of the components of diffusion processes. And this can be just kind of like, what kind of terms or what kind of things come to mind now that we've heard a little bit about diffusion. You can maybe just type into chat some ideas, some words. It doesn't need to necessarily be a complete definition about, the conservative material moving through space in a rate proportional to time or whatever. I mean, it just, what terms come to mind now when we talk about diffusion? Okay, we got flux. So thanks. At least we have one bold individual willing to say something. So yeah, flux. We talked about fluxes of material and conserving mass, conserving energy, whatever it is. What else do we have that relates to to diffusion. Goes from high concentration to low concentration. Yes, exactly. So we saw that example with the atoms of A moving off to the right from the area where they're highly concentrated to areas where the concentration is lower. Same thing happens with heat transfer, as mentioned with the kind of hot material being put in contact with something cold. So that, yes, this flux of material, or flux of energy will go from high to low concentrations. Anything else that comes to mind for diffusion processes? Anything about the word gradients? So it's okay if there's not, but yeah, the one other thing that's maybe useful to consider here in terms of a diffusion concept is that diffusion reduces gradients. So whether it's applied to things like if you have an escarpment at the Earth's surface, a good example would be some of the wave-cut terraces that were formed by different levels of, or different relative sea levels in the past. For instance, these can be found in many places where there's been significant post-glacial uplift, including Finland and Norway, Sweden, other places like that, parts of Canada as well. You can find past sea level indicators in the forms of these kind of wave-cut terraces at different elevations above the current day sea level. And as you go from younger to older, what you tend to see is that the escarpment has been diffused away so that they're less sharp for the old ones and more of a sharp escarpment for the newer ones. So that's another example of this concentration gradient idea, or the gradient in general. In this case, it's a topographic gradient being reduced by diffusion of material as the surface erodes. The other thing here are some geological examples where diffusion might apply. Let's get a couple, and then I'll give you a little break here and we can come back in a few minutes. But let's get a couple examples of where diffusion might apply to some geological process first. I mentioned a couple at the beginning of class, but maybe you even have some other ideas yourself of things where diffusion could be important. So this is the difficult thing about being on Zoom, that I can't sort of make you uncomfortable by staring at you in a classroom, make you sort of feel like you should say something. But how about, can we get one example? Rain splash. Okay. So yeah, we didn't really look at it in any detail. I've actually, there's some old slides from previous years of the course where you can see a kind of example of some scientists who are studying rain splash in a laboratory by dropping water droplets onto a sort of variably sloping surfaces and watching how the little sand grains that they sprinkled on the surface got splashed away. But yeah, rock and fluid interactions is another place exactly where diffusion might occur. And there are plenty of other examples of diffusion as a process. It's a very general process. So whether we're talking about rheology, whether we're talking about heat transfer, whether we're talking geomorphology or petrology, diffusion occurs in many different ways at many different scales in the earth sciences. So we'll learn about how to deal with the diffusion equation in the context of thermochronology. But what you'll see is that you can take the same equation and just change some of the constants, and suddenly you could apply that same equation to modeling hill slopes and other kinds of things very easily, modeling heat transfer or whatever. But yeah, at this point, why don't we take a 5-minute break? So I've got, let's make it a 5.5-minute break. So we'll come back at 3 o'clock sharp. and we'll continue on with talking about thermochronology at that point. So see you in 5 or so minutes.